Good morning, students. Today I am going to speak on the topic thermodynamics. In that, we are going to consider thermodynamic potentials like internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. Now, what are their significance? Then, condition for equilibrium of phases in terms of Gibbs potential. So, now let us define one by one. The first one, thermodynamic potential. First one, internal energy. So, represented by U. It is the total energy of a system. So, according to the first law of thermodynamics, we know that the mathematical form is given by dq is equal to du plus dw. So, this will be equal to du plus, so dw is nothing but pdv. So, our du will be equal to dq minus pdv. And from the second law of thermodynamics, we have dq is equal to TdS. So now substituting dq in this expression, we get du equals TdS minus pdv. This equation gives a change in internal energy of the system in terms of thermodynamical variables, pressure, volume, temperature and entropy. So second one, Helmholtz free energy represented by F. It is defined as F equals U minus Ts. Since U, T and S are state variables, F is also a state variable. According to the first law of thermodynamics, we have du equals Tds minus dw. If the temperature is maintained constant, so then we can write Tds equals d of Ts. Therefore, du equals d of Ts minus dw, or du minus d into Ts will be equal to minus dw. So now taking d common, d into u minus Ts is equal to minus dw, and writing u minus Ts as F, we have dF is equal to minus dw, where F is known as Helmholtz free energy. So the change in the Helmholtz free energy is given by dF equals du minus d into Ts. So dF equals du minus Tds. Differentiating this, we get minus T ds minus S dt. But we have Tds is equal to du plus dw. Substituting this, we get dF equals du minus dw minus S dt. Simplifying this, we get dF equals minus pdv minus S dt. This equation gives the change in Helmholtz free energy in terms of thermodynamical variables P, V, T and S. So next the third one, enthalpy. So enthalpy is represented by H. It is the total heat and given by H is equal to U plus PV. Since U, P and V are state variables, H is also a state variable. The change in enthalpy is given by dH is equal to du plus pdv plus vdp. dH equals dq plus vdp, where dq equals du plus pdv. So then the equation becomes, and also we have dq equals Tds, therefore dH equals Tds plus vdp. This equation gives the change in the enthalpy in terms of thermodynamical variables P, V, T and S. So next, the fourth one, Gibbs free energy represented by G. It is defined by the equation G is equal to H minus Ts. The change in Gibbs free energy is given by dG equals dH minus d into Ts. So then simplifying, we get dG equals dH minus Tds minus SDT. But dH equals Tds plus vdp. So then we have dG equals Tds plus vdp minus Tds minus SDT. So plus Tds and minus Tds gets cancelled. We get dG equals vdp minus SDT. This This above equation gives the change in Gibbs free energy in terms of thermodynamical variables P, V, T and S. So next, any mechanical system is in stable equilibrium when it will be in stable equilibrium only when the potential energy of the system is minimum. This implies that the system must proceed in such a direction so as to acquire minimum potential energy. So similarly in thermodynamics, the behavior of internal energy, Helmholtz free energy, enthalpy and Gibbs free energy is similar to potential energy in mechanics. For example, in an isochoric adiabatic process, internal energy is minimum. Similarly, in case of isobaric adiabatic process, the enthalpy is minimum. In the same way, in case of isothermal isochoric process, the Helmholtz free energy also minimum or tends to minimum, and in an isothermal isobaric process, Gibbs free energy tends to a minimum. So next let us consider the condition for equilibrium of phases in terms of Gibbs potential. So for that, let us consider a liquid in a closed system which is in equilibrium with its vapor. The temperature and the pressure being equal in both the phases of the substances. As each of the phases are in equilibrium, the temperature and pressure remains constant. Therefore, the thermodynamic potential are equal to the product of specific values and mass of the substance in that phase. So consider or let M1 and M2 are the masses of the substances in different phases, that is liquid and vapor respectively, and G1 and G2 are the specific values of the Gibbs potential in the two phases. So then for the entire system, G equals M1 G1 plus M2 G2, call that equation 1. So now let a small quantity of liquid changes into vapor without disturbing the equilibrium, and then let us differentiate the equation 1. So we get delta G equals delta M1 G1 plus delta M2 G2, call that equation 2, where dG gives change in Gibbs potential. Delta M1 and delta M2 are the changes in the masses of liquid and vapor phases of a substance. But the system is closed. The changes takes place at constant temperature and pressure. Hence the process is isothermal and isobaric. Under this process, the change in the Gibbs potential, that is delta G, will be equal to 0. So therefore we have our equation 2 becomes delta M1 G1 plus delta M2 G2 will be equal to 0. Since the system is closed, the conversion of liquid to vapor phase does not change the total mass of the substance in it. So the amount of decrease in the mass of the liquid is equal to the amount of increase in the mass of the vapor. So therefore we have delta M1 will be equal to minus delta M2. Substituting this and simplifying, so finally we get G1 equals G2. So this shows that the thermodynamic potential are also the same in the two phases of the substance which are at equilibrium. So in other words, we can say that if any two phases of a substance are in equilibrium, then the thermodynamic potential, that is Gibbs potential, are also the same in the two phases. Thank you.